Welcome back. This is the day the Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about the right-hand rule and talk about some applications associated with magnetism. So, big idea. The idea is this. If there's a charge or a current moving through a magnetic field, as it moves through there, it's going to experience a force that's going to try to deflect it off its path in a perpendicular motion. What that means is if we had a magnet, two magnets here, north end, south end, we got the magnetic field pointing from right to left. If a positive particle was moving perpendicular through the field, so if a positive particle is moving up, it would experience a force because of going through this field. So the theory behind this is there's basically there's already a field present, a magnetic field from the two magnets, and the particle itself produces a field, and so therefore, while it moves through, it's going to be pushed or deflected off course. All three of these things are going to be perpendicular to one another in the cases that we deal with. Now, of course, in real life, you may not have like a particle moving perpendicular directly through, a magnetic field. They might be moving at a 45-degree angle or something. So when you go on to future level physics courses, they might have like, the angle, it's at this angle moving through it. And then that's pretty much the same stuff we're talking about today, just putting in a sine and cosine aspect to it. But anyway, big idea, as a particle moves through a field, as long as it's a charged particle, or if it's current, because that really is just charged particles, the idea of a charged particle moving, and if it's moving perpendicular to a field, it's going to be deflected, and these things are all perpendicular. So, this is called the right-hand rule. The right-hand rule helps us determine where everything is going. So, your thumb, when using the right-hand rule, is going to be whichever way the current or the particle is moving. So in our example here, we have the particle moving up, moving vertically. We have the field pointing from right to left. And so my thumb, again, is going to be which way the particle is moving. My hand, my fingers are pointing towards which way the field is moving. Then the force will be whichever way your palm is facing. So in this case here, you see that the force is pushed. Again, here it's a second finger. Sometimes people say use your finger. I just say the palm. So whichever way your palm is facing, that's which way it's going to feel. So as that particle moves up through this field, it would be pushed towards me out of the page. All right. So again, this is just in words. The thumb is going to be your current or the velocity of the particle. Your fingers are going to point whichever way the B field, the magnetic field is, and your palm is going to be whichever way that it's going to be pushed, whichever way it's going to be deflected. So you use the right-hand rule when you're dealing with positive particles or a positive current. If it's negative, you can do the same thing, but use left hand. So again, thumb would be the velocity or the current of the negative. The fingers would be the magnetic field, and the palm would be which way it's pushed. Okay? Some equations here for us. How strong is that force that it feels? The force depends upon three things: the magnetic field strength. If it's a current, how big is the current? And how long is the wire that's passing through? If it's an individual particle, magnetic field strength still, but instead of the current, the velocity, and then the charge in coulombs of it. So first equation, force equals Bill, magnetic field times current times length. Second equation, QBB, charge the particle in coulombs, velocity of it, and then the magnetic field strength. So this equation here is useful to find out what the force actually is that's going to be pushing it around. So just some quick applications of this. This is how speakers work. So again, if you have a speaker, obviously you do because you're listening to me talk. How does that speaker work? Pretty much what's going on is it moves electrons through a wire, has an electromagnet in there next to another magnet. So inside by that speaker, there's a permanent magnet, and then they have a solenoid inside there, which pretty much means just a loop of wires, and they can run a current through that. And when you move a current through those wires in between the magnet, it's going to cause those wires to want to be pushed around. And that's how the wires push in and out of the speaker. And so what they do is they use an alternating voltage, an alternating frequency, where like they keep shifting which way the electrons are moving. That way the electrons push out, push in, push out, push in, because it changes the direction. So back to this idea up here. If we have the positive particle moving up in the field, first it'll push towards me. If we turn it around to move the other way, then it pushes out. So all it does in your speakers is it just has a permanent magnet as like right here, and inside there, you move a current in some wire. And that wire is going to be pushed or pulled away, which are based off which way the current's moving, as long as it's in that field. And as it fluctuates back and forth, what's going to happen is it's going to push on the speaker head, which we interpret as sound in. If you want a higher pitch, you just make sure that it changes back and forth faster, so you just alternate this a little faster. If you want a lower pitch, it just alternates slower, so that it pushes out and pulls back, a little bit slower pace. So anyway, this is an important math equation for you to solve some of the stuff related to how strong is that force actually. This is for individual particles for the force it feels. Some of the stuff at the A level, you have to actually figure out what kind of acceleration it has. So again, just connect that to the force equals what? Mass times acceleration. If you know the mass of the particle, you can find the acceleration of the particle, and it's going to accelerate as it goes through the field. So the difference between the A and B is going to be solving like, can you take this connection here to some of your first semester kinematic stuff? All right, here's just another picture of that. So again, we have a magnetic field being generated. If you have a particle moving up, it feels a certain force towards us because, again, this is the idea is that it produces its own field, and that's where it comes from. But really all we're going to care about here is that what does everything stand for, and find those things here. Now, some other applications besides speakers would be mass spectrometers. A mass spectrometer basically is a way to find out how heavy an atom is. So it can be used to separate ions into different isotopes. Basically what happens is we take some atoms and we ionize them. So this can be done by just firing electrons at them so they gain extra electrons, or putting them through a bunch of X-rays so that they lose their electrons so they're positive. In either case, we just charge the atom. Then we send the charged particle into a magnetic field, and the magnetic field is curved here. We have a curving path because what's going to happen as the charged particle comes into the field is going to want to bend. And so we bend with it. The magnet bends with it, so that continues to be basically perpendicular. And what happens is we get different levels of deflection based off how heavy the material is. So a heavier atom is going to not be deflected as much because it's more massive, so it's harder to deflect. And a lighter one's deflected more. You can just think of this like throwing a baseball into the wind or throwing a ping pong ball into the wind. The baseball being heavier is going to be less affected by the wind, and the ping pong ball is more affected. And so the light molecules that come in are going to deflect more, and the ones that deflect less are heavier. And so then we get a range here. It might be better to think of it like just with CO2. All right, so we could find CO2s at different masses. We send CO2 through here, we ionize it, and what goes into this field here, what's going to happen is the heavier ones, so like if there's a carbon with like 14 mass rather than 12, we'd have a mass of 46. So CO2 with the mass of 46 deflects a little less. The one that's lighter deflects a little bit more. And so we can connect this to finding out what the actual element is, or the molecular size too. So a mass spectrometer is just basically ionize the particles, ionize the molecules, send them through a magnetic field, let that thing deflect. Based off the level of deflection, we know how heavy you are through a bunch of math. So other cool things about the idea that it can bend is particle accelerators. So there's two different types of particle accelerators. There's circular ones, cyclotrons, and there's linear particle accelerators. The ones that get up to real high speeds tend to be the cyclotrons. What they do is they basically, this would be like the Large Hadron Collider too. What it's going to do is it's going to get some particles moving along this path here, and as it goes in, there's a magnetic field that's going to cause it to bend. And so basically a magnetic field causes it to bend around these corners. And then it's alternating the voltage. That way it wants to bend the other direction. And it gets wider and wider because it's going faster and faster because it keeps getting accelerated. What they do is we accelerate the particle between here, and then it gets faster, and so it needs a larger curve to get around because it keeps getting accelerated and curving around. And so finally it gets really big. So, and through a whole bunch of like right-hand rule and bending it, eventually the electrons or whatever's inside there comes out with a high speed. This works a little different than linear accelerators, but one last picture of this. Again, big idea. We have some magnetic field that's going to cause these charged particles or electrons to want to get speeded up. And so they're going to follow this path as they get sped up across the gap. They're going to get faster and faster, and then therefore require a bigger curvature to turn around until eventually it comes out really fast. A linear accelerator doesn't curve. It doesn't use a magnetic field. It just alternates positive and negative voltages. So you start off with a charged particle, and you have this negative, and then as soon as this particle enters the negative, they alternate the voltage, so this becomes positive, this is negative, so the particle wants to go to the next one, and then as soon as it hits it, we alternate it again, so it wants to push on to the next one, and it just gets longer and longer because it gets faster and faster, and so they have to basically do a lot of math to figure out what is going on there. Another cool look, and how this is actually used in real life too, for these particle accelerators, is like cancer treatments. Like, how do you fire electrons at somebody so that they can, be cured of their cancer? Basically, what we do is we get some particles going really fast, and then we fire them at the person's body. And so imagine going to the doctor's office and they want to treat you for a cancer, and you got some tumor. What they're going to do if they use this kind of treatment is they're going to sit you down somewhere, lay down. They're going to cover your whole body with some shielding, like, some tungsten, some lead shielding, and leave one little spot open. And then they're going to have some particle accelerator, which just gets these particles, electrons up to high speeds, and then they're going to shoot them at you. And when they hit the tissue, they're going to kill it. So it doesn't hurt till later. All right. So, but that's, again, another example in real life how these are used. So now a velocity selector is really important because it allows us actually to choose what speed we want. And this would be important for like medical uses. We want to know exactly how much energy, because energy is connected to velocity, is hitting the person, because that's like how deep we want it to go into the person's body. All right, so if you want to penetrate deeper, you got to give the particles more energy to penetrate further. So a velocity selector helps us determine what speed we want actually coming through. So the way it works is it's going to use the right-hand rule, but it's going to have one more thing to it. So it adds on its own a capacitor, basically, an electric field generated. So we have the magnet from before, we're going to send a particle through it, but now instead of just having a magnetic field, we also have positive negatives. So we have actually an electric field too that are perpendicular. And so if you think about what's going to happen, the positive particle, if you send it into the electric field, if it's going really slow, what's it going to do? It's going to fall towards the negative, because that's what it wants to do. It's just going to fall towards the negative. If it goes too fast, though, the faster it goes, again, right-hand rule, that positive particle coming in, the field we have pointing towards the south there, as drawn, what's going to happen is that particles will be deflected up because of the force that is being generated by it moving through a magnetic field. And so if it goes too fast, it goes up. And only at the right speed will the particle go through, because the force from the positive one going down to the negative, balanced by the force being pushed up as it tries to go through, bounce out at some place. And that equation here is E over B. So to find the actual velocity you need, it's just a ratio of how strong is my electric field, how strong is my magnetic field. And so E over B tells us what velocity we need to get through here. So if we want to, again, back to treating cancer, we could say, well, we want to have, more energy or something, a higher velocity, and so they can adjust the electric field strength, and that's just capacitors, or they can change the magnetic field strength too. So they just change those things to get the velocity they want, so to get the energy it needs. Again, big idea here, it has to be balanced. So positive particle going through, if it goes too slow, it's going to want to fall to the bottom. If it goes too fast, it deflects too much. And if it's balanced, it goes straight through, and we can select the velocity we want. There's just another cool thing too here. We can find the speed of your blood and your arteries by just ions moving through it, creating a field. So the general idea is I have arteries moving through my body, and they're carrying a bunch of sodium and chlorine and other positive charges. And so we have a current going through my arm. All right. And so with a very, very sensitive devices, we can actually measure the blood flow rate, because they will produce a field which will cause a deflection. So that's kind of neat too as well. All right. To finish here, I want to talk about right-hand rule again and just do some samples. We're going to assume a positive particle for these things here. Let me make myself a little bit bigger here. All right, so for the first example, we have a particle, and we're going to assume a positive particle moving to the right. And we have a force that's going up. The question would say something like, what is the magnetic field? Where's it going? So my thumb is the velocity. My force is the palm, palm's facing up. So where's it going to be going? Then where's the magnetic field pointing? Magnetic field is pointing up. For convention, you'll sometimes see that we have X's and we have some dots. The X's, these ones mean that, think of it like an arrow. These are the feathers of the arrow. If you're shooting into the board, if you see an X, that means the field is pointing into the board. If you have a dot in a circle, that's like the tip of the arrow is coming towards you. So for B, we're saying that the force is going into the board, away from me. All right, so right-hand rule, our velocity is going to the left. The force is going into the page. Which way is the field facing? Field is pointing up. For C, now we're told the velocity is going into the page. We're told that the force of field is to the right. So which way is the field pointing? Well, you know, it's still up. All right, this one, our velocity is towards us. So coming towards me, I have the particle's velocity. The force it's feeling is to the right. Okay, how am I gonna do this? Ah, there we go. Which way is the field pointing? It's pointing down because the particle's moving towards me. Field's pointing this way where my palm's facing. Field's pointing straight down. Here we have the magnetic field pointing up. That's my fingers. The force it feels is going to be to the left. Which way is the particle moving? Coming towards me. It's coming out of the page towards me. Here we have the field pointing towards me. So my fingers point towards me. Force is down. Which way is the particle moving? Going that way. Do some with some other ones here. These are just with the lines drawn. Which way is the force being felt? We have a positive particle moving to the right. The field is pointing up. Which way is the force? Coming out of the page towards me. Now we get a negative particle. The difference between a positive and negative is just use your left hand. All right. So we have the particle moving down and it's negatively charged. The field we're saying is pointing into the page because those X's mean into the page because dot means coming towards us. Which way is the force feeling? It's going left. All right. Here we have the current, and current is positive. So our current is going to be going towards us. Our B field is going to be pointed into the board. So let's see how we can do this here. Current, oh man. Current comes towards us. Magnetic fields, can we do that even? Oh man, maybe it's a tricky one. Don't think my hand bends like this. This must be a fake one to put on there. All right, because yeah, of course it would be. They're in opposite directions. These things are always perpendicular to one another. Whew. All right, so that's not possible. So, all right, to find the force actually, which means it doesn't exist. All right, hope that helps you out. Godspeed.